Alright, gang, welcome back to GO2. So we are moving along with material, and we're starting with lecture number 7 today, PowerPoint number 7. It's titled The Carbon Cycle, and so far we've sort of established how climate works on an instantaneous level. If you look at the climate, what factors are controlling the distribution of water in the atmosphere, the distribution of wind currents, ocean currents, how that affects precipitation, the distribution of forests, deserts, etc., and temperature. And so that's sort of this instantaneous snapshot of the climate. Now, the course title is Earth's Climate Through Time, and so the rest of the quarter we're going to talk about what controls climate on longer time scales, and how does the Earth respond to changes in climatic parameters, and what feedbacks control it on long time scales and keep us within this range between 0 and 100 degrees C, where we have liquid water existing at the surface of the planet. Okay, and so we established this that there's energy coming from the sun in the form of both visible and infrared radiation. Some amount of it gets to the Earth. The Earth then emits radiation back out into space in the form of infrared radiation. Remember that all objects in the universe emit radiation. And so some of the incoming solar radiation is blocked, but most of it gets through. Lots of the outgoing infrared radiation, on the other hand, gets blocked. And it gets blocked or absorbed, really, more specifically, and re-radiated. Much of this happens by water, but what we learned was that water is a direct function of temperature, and so the warmer the atmosphere, the more water it will hold. So it's not really an independent variable there. CO2 is an independent variable. It absorbs a significant amount of radiation in a really important part of the spectrum here, where water isn't absorbing fully. And CO2 is not a dependent variable or a dependent parameter, right? It's independent. CO2 can change independently of temperature. Okay, and so the Earth is at some sort of a steady state, and so there's there's solar radiation coming in, and there's infrared radiation going back out, and the flow in equals the flow out, right? So that's just like this little jar with the green water in it that I set up. We have some flow in and we have some flow out, and there's some amount of water, or in this case energy, in that reservoir. Now if we partially close that valve on there, what we found is that the water level increases until the pressure pushing down, the hydrostatic pressure, forces enough water out of this nozzle to again equal the inflow. So inflow equals outflow, and then we're back at steady state. But the amount of water in the reservoir increased, and the residence time increased. The same is really true of the climate. CO2 acts just like a valve that lets infrared radiation out of the atmosphere. Infrared radiation collides with CO2 molecules. It's absorbed, and some amount is re-radiated back downward. And so it keeps that energy in there longer. And so if you increase the CO2 concentration in the atmosphere, the amount of infrared being redirected back down toward Earth increases. And so it's just like closing that valve, and the amount of energy in the system increases, just like we had an increase here. We'll find another steady state. It'll just be in a place where the reservoir size, the amount of energy in the reservoir in this instance, is higher, right? Which means higher temperature in this case. Okay, so what controls CO2 in the atmosphere? Well, carbon, as you probably know, is everywhere in the environment. You can find it in all kinds of different places. We are carbon-based life forms. Life on this planet is carbon-based. That is, the people say that, but it's really true. You know, these are. See, we divide carbon compounds into two classes: organic and inorganic. And these organic molecules over here are mainly they're mainly associated with life. They're molecules that life is assembling here, like glycerol, glucose, fatty acids. Octane here is a hydrocarbon. They're really different than inorganic carbon molecules like CO2. This is the bicarbonate ion, carbonic acid, minerals like calcium carbonate or magnesite. Very different, and so we'll talk more about those as we move through here. We'll start with the organic carbon side of things. Organic carbon is, like I said, generally associated with or produced by living things. That is not to say that living things can't produce inorganic carbon. They can, as we'll touch on briefly. But organic carbon compounds contain lots of carbon-carbon bonds. As you can see here, you can write out a chemical equation like this. This means we have 3 carbons, 8 hydrogens, and 3 oxygens, but they're bonded together in a specific way. And it turns out in glycerol, it's like this. There are these 2 bonds here between carbon-carbon and carbon-carbon. Similarly, in glucose, there's a ring of carbons. In fatty acids, there's basically just a chain of carbon-carbon bonds, and it can be effectively any length. This is an example of the simplest, where we just have two carbon hydrogens in the middle here. You could extend that out to as long as you want, really. Octane is a saturated hydrocarbon, so it's just a chain of carbons, right? Lots of carbon-carbon bonds, lots of carbon-hydrogen bonds. That's organic carbon. And the reason that bonding is like that is because carbon is in its reduced form. Okay, and we'll explain more what that means as we move through here, but that's really important here. Carbon is reduced. All right. So inorganic carbon, on the other hand, is generally not formed through life, through biology. It's generally formed through abiotic chemical processes. It's things like carbon dioxide. That's an example of inorganic carbon. The bicarbonate ion or carbonic acid. These minerals like calcite, magnesite, those are carbonate minerals. Calcium carbonate is limestone. It's precipitated by living organisms, right? A clam produces a shell, for example. The shell itself is not organic carbon. It's inorganic carbon. It's carbonate. The biological material, the fleshy tissue, is organic carbon. That would be reduced carbon. But as it says here, carbon in inorganic carbon compounds is in its oxidized form, and it generally does not contain carbon-carbon bonding. Okay, so what does oxidized versus reduced actually mean? Well, redox reactions are a class of chemical reactions that involve transferring an electron, okay? That's all it means. It sounds complicated, but it's really not. All it is a chemical reaction where an electron is transferred, okay? And something gives up the electron and something receives the electron, all right? Oftentimes this involves shifting around some oxygen and hydrogen as well. And so in this example here, we have octane reacting with oxygen to form carbon dioxide and water, right? And so the carbon here is going from this carbon-hydrogen compound into carbon dioxide, okay? And so that involves giving up an electron, okay? And so it is being oxidized, is what we say. And so in the compound that receives the electron is said to be reduced. In this case, oxygen is receiving the electron, it's being reduced into water, and the compound that gives up the electron is being oxidized. In this case, octane is being oxidized into carbon dioxide, okay? This reaction, if you didn't already know, is combustion, right, of gasoline. Octane is gasoline, so that rating that you see on the pump, 86 or 80, 89 or 91, that's referring to the amount of octane in the fuel. And what you're doing when you operate your car or when you burn anything, you're oxidizing. And so there's obviously a lot of energy that comes out of this reaction. Redox reactions are all about energy, right? And life is all about energy. Life is all about chemical energy, and chemical energy is all about redox, right? So life is all about redox reactions. Redox reactions really are the base of life. It's the currency, the energy currency that we use. Okay, and so they're really important, obviously. 2 very important examples of redox reactions are photosynthesis and respiration. And so in photosynthesis, organisms are taking carbon dioxide and water and turning them into glucose, so sugar, and water. I'm sorry, and oxygen. Right, so they're taking CO2 out of the environment. They're oxidizing this water into oxygen, and they're reducing the carbon dioxide into organic matter, glucose. All right, respiration is the exact opposite, right? So this reaction requires energy to come in the form of sunlight. This reaction here, respiration, you take glucose, sugar, and you oxidize it into CO2 and water, and you get energy out, right? That's why we breathe in oxygen and breathe out CO2. That's why we eat food, right? That's to gain energy. right? So photosynthesis, again, uses carbon dioxide and water with some enzymes and some energy from sunlight to reduce carbon dioxide into sugar. In the process, it creates oxygen as a byproduct, right? O2. Respiration does the opposite. It takes glucose, C6H12O6, and it oxidizes it into carbon dioxide and water, and it generates energy, right? That's sort of the key to this, is that it generates energy. That's why we do it. It uses oxygen to do so, reducing it back into water, right? So it consumes oxygen, right? It's just like combustion, right? Octane plus oxygen goes to CO2 and water. And here we have glucose and oxygen going into CO2 and water. They both produce energy. If we could do combustion, on a very small scale, we probably would. I mean, effectively, that is what we're doing, right, on a cellular level. Okay, and so we have these two extremely important redox reactions. In reality, it's really just one. It's the same thing, right? CO2 plus water turns into glucose and oxygen. If you're going this direction, you're what we would say fixing carbon. You're taking carbon dioxide and reducing it into organic matter. That's photosynthesis, and it requires the input of energy in the form of sunlight. If you're going this direction with it, you're taking glucose and combining with oxygen to form carbon dioxide and water. You're doing respiration, and you're gaining energy in the process. Okay, so photosynthesis converts atmospheric CO2 into sugar. Life then takes that sugar and it produces all kinds of different complicated compounds like amino acids and fatty acids, carbohydrates, right? And then respiration takes all of those complicated organic compounds and it just converts them back into CO2, right? This is all coming from the atmosphere, right? And so you have atmospheric CO2 being fixed into organic matter. It spends some amount of time in this living and dead organic matter reservoir before it's returned to the atmosphere through respiration, right? This is the short-term carbon cycle. All biomass, both living and dead, was once carbon dioxide. It's produced through carbon dioxide, mostly through photosynthesis. And eventually it will all be converted back into CO2, largely through respiration, if not through respiration, through some form of weathering or metamorphism, topics we'll touch on as we move forward. All right. So in addition to organic reactions, carbon also obviously participates in a lot of inorganic reactions. Okay, and so we gave you some of these compounds here: carbon dioxide, bicarbonate, carbonic acid, the carbonate ion, carbonate or calcium carbonate, and magnesium carbonate. Those are minerals. Okay, and so we've briefly touched on this. I've mentioned it, alluded to it multiple times already throughout the quarter, but to give you, to go into detail here now, the inorganic carbon cycle works like this. As rain falls through the atmosphere, it precipitates. Water precipitates from the air, and it forms raindrops. All right. As those raindrops fall, they absorb carbon dioxide out of the atmosphere. Carbon dioxide dissolves into the water, and when it does that, it forms carbonic acid, H2CO3. Okay. When that rain when the rain falls, it absorbs the carbon dioxide, creating carbonic acid. When that lands on rock or on the land somewhere, that carbonic acid is able to react with the rock itself or with the substrate that it lands on. And so it does that. It lands on it, it reacts, and it causes dissolution. It chemically starts to break down the rock that it's reacting with, and turn it into dissolved ions that are then transported through streams and rivers. And so in this instance here, this is sort of a simplified example. We're taking carbonic acid reacting with this calcium silicate. This is a mineral called wollastonite. It's not important what that mineral is, but it's a silicate rock, okay, a silicate mineral. It's calcium silicate. I'm using a simple one because we want this calcium ion, but this applies universally to rocks that rain interacts with. So we're taking carbonic acid reacting with a silicate rock, calcium silicate, and it's dissolving to produce calcium ion, bicarbonate ion, and dissolved silica. All right, the dissolved silica is not super important, but we're really, really interested in this calcium and this bicarbonate, okay? Because remember, we took CO2 out of the atmosphere and dissolved it into rain to produce carbonic acid, okay? And then that carbonic acid is giving up a hydrogen, giving up a proton in order to react. And it's producing calcium ion and bicarbonate ion. So we've now taken a CO2 out of the atmosphere and we've turned it into bicarbonate, all right? That's important because rivers are going to carry the calcium and the bicarbonate to the ocean, okay? And when it gets to the ocean, the calcium and the bicarbonate can react to precipitate limestone or calcite, this mineral here, calcium carbonate, okay? So calcium and carbonate ions in the ocean can react to form limestone, a rock that can last for millions to billions of years, all right? So now we've taken carbon dioxide out of the atmosphere. We've let it dissolve into rainwater to produce carbonic acid. We've let that react with some rocks to form bicarbonate ion and also liberate some cations here, where it reacts in the ocean to form calcium carbonate or magnesium carbonate or iron carbonate, some type of carbonate mineral that precipitates and forms deposits on the seafloor. Okay, and so those carbonate sediments remain on the seafloor until they're subducted back into the mantle, where much of the carbon is going to be volatilized and returned to the atmosphere through volcanism and metamorphism. Other forms of volcanism like hotspots, mid-ocean ridges, etc., also emit CO2 to the atmosphere. Okay, and so here we are with the long-term carbon cycle. Okay, so we talked about the short-term carbon cycle. Now we've talked about the long-term carbon cycle. In the long-term carbon cycle, atmospheric CO2 is converted back into carbonate rock. First, this occurs by dissolving into the rainwater. Then that reacts with exposed rock. And then finally, it combines with calcium or another suitable cation to form a carbonate rock. So that's described kind of by these three equations here. CO2 plus H2O turns into carbonic acid. Carbonic acid plus calcium silicate turns into bicarbonate, calcium ion, and dissolved silica. And then the bicarbonate recombines with the calcium to form calcium carbonate. Okay. This word here, cation, just refers to a positively charged atom or molecule. An anion is a negatively charged atom or molecule. That's important, those terms there. Okay, so it turns out that this is a little bit of an oversimplification. All right, and I'm going to tell you what actually happens, but on the surface level, right, at the sort of 30,000 foot view, this is the long-term carbon cycle. CO2 in the atmosphere forms acid when it reacts with rain. That acid weathers rock, delivers material to the ocean, dissolved material to the ocean, where the end product of the CO2, right, this bicarbonate ion can precipitate into a solid form with another atom and remain there. Okay, so we've taken atmospheric CO2, gaseous CO2, and turned it into a solid phase. All right, that's really important. Now, in reality, what's actually happening is that when carbon dioxide dissolves into water, it first forms carbonic acid. Okay, like it says right there. First forms carbonic acid. The carbonic acid dissociates into a hydrogen ion and a bicarbonate ion. Okay, it just loses one of these hydrogens. All right, now pH is a measurement of acidity, right? pH, like this, little p, big H, right? And pH of 7 is neutral, right? pH of 1 is extremely acidic. pH of 14 is extremely basic, right? H here refers to H plus. It's percent hydronium ion, or you could also write it H3O. People write it that way also. Whoops, not like that, of course, like that. But it's really percent hydronium. So it's pH. It's percent H plus. So if we're producing an H plus, that literally is acidity. All right, that's what we're measuring when we measure acidity. We're measuring how much hydrogen ion is in the solution. And so when the carbonic acid dissociates into bicarbonate and hydrogen ion, it's making the rainwater more acidic. Okay, bicarbonate can further dissociate into more hydrogen ion, and this ion here that is the carbonate ion. Okay, that again will put more of that hydrogen ion into solution. Okay, now this little kind of equation here it reflects this process. Carbonate equilibrium is what we call it. Okay, CO2 is in equilibrium with carbonic acid, which is in equilibrium with bicarbonate, which is in equilibrium with carbonate. All right, now the relative amounts of these three, oh, what did I just do? I guess that was already red, maybe. Let's make that black. It should be red. So these four things are in equilibrium. Really, these three here, and the amount of CO2 that dissolves into the solution is relative to the amount in the ambient environment, right? But the amount of these three relative to one another is going to be determined by the pH of the solution. At a higher pH solution, so a more basic solution, is going to be dominated by this carbonate ion. Low pH acidic solutions are going to be dominated by carbonic acid over here. Solutions that are around neutral, near pH 7, are dominated by the bicarbonate ion, okay, this middle one. And again, right, CO2 dissolves into water, and it initially produces this, carbonic acid. Now, if the solution is around neutral, most of that carbonic acid dissociates and turns into bicarbonate, okay? Let's see here, get me out of that. There we go. Okay, so as rain falls, it starts its life at pH 7, neutral, right? It's pure water. And as CO2 dissolves into it, it forms carbonic acid, which dissociates almost immediately into bicarbonate ion and hydrogen plus. Okay, hydrogen ion, because the solution's around neutral. All right, but then there's no longer carbonic acid present. So more CO2 is able to dissolve into the water, right? Because these two here are in equilibrium with one another, okay? And so as more CO2 dissolves into the water, it dissociates because it forms carbonic acid, dissociates into hydrogen ion and more bicarbonate. Okay, and this process continues, but as it continues, acidity is building up, right? Hydrogen ion is building up in solution, and that's causing the pH to go down, which when the pH is lower, more of the carbon that exists in the solution is existing as carbonic acid, okay? And so this is going to progress until the concentration of carbonic acid is in equilibrium with the ambient CO2 concentration, all right? And that might seem complicated and maybe needlessly overly complicated, but it's not. It's actually really important, right? Because one of the major problems with global warming or climate change, human-induced climate change, is ocean acidity, ocean acidification, right? And so when let's see, I think somewhere I've got a slide that's going to say this. Yeah, CO2 has the potential to dissolve directly into ocean water, right? The same carbonate equilibrium process applies, and since seawater is pretty close to neutral, most of the CO2 that dissolves into ocean water dissociates to become bicarbonate, right? And in the process, it produces hydrogen ion, which causes the solution, ocean water in this case, to become more acidic, all right? That's really important. Okay, but bringing it back to here, we have rainwater falling, becoming more acidic as it falls because it's absorbing carbonic acid, which is generally dissociating into bicarbonate and hydrogen ion. The hydrogen ion has the ability to react with rocks and break them down, right? And so that's really the process that we're most interested in here. CO2 plus water turns into carbonic acid, which then turns into bicarbonate and hydrogen ion. The hydrogen ion, the acidity, reacts with the rock, causing it to dissolve. So in this case, we have our calcium silicate again, dissolving as it interacts with hydrogen ion to produce calcium and dissolved silica. Okay, so this uses a simple silicate mineral, like I said, wollastonite, containing only calcium and a silicate ion. It applies generally to all rocks. All right, and so carbonate rocks like limestones, this mineral calcite, right? It can dissolve also, and it turns out it dissolves really rapidly. If you took a piece of granite and a piece of limestone and you put some acid on each, some hydrochloric acid or something like that, nitric acid, what you would see is that the carbonate rock would fizz and bubble aggressively, dissolving very rapidly. The silicate rock would do nothing. The granite would just sit there. But over longer time scales, it dissolves. Dissolving a carbonate rock will accomplish the same thing, right? You can take CO2 and you can dissolve it into rainwater. You can use the acidity to dissolve a carbonate rock, calcium carbonate, and you'll accomplish the same thing. You're taking CO2 and you're putting it into the ocean, right? But you're dissolving a carbonate rock to produce one calcium ion here, and then you're recombining that one calcium ion to produce the same carbonate mineral. And so by dissolving carbonate rocks on long time scales, you don't actually achieve any reduction in CO2, right? This is all about reducing CO2 levels in the atmosphere, right? Not reducing it through redox reactions, lowering the CO2 level in the atmosphere, because we're taking atmospheric CO2, we're reacting it with rocks, and then we're precipitating it as limestone in the ocean, right? And so every molecule here of CO2 that ends up as a molecule of carbonate locked in limestone is one less in the atmosphere, right? Okay, and so if we do that with a carbonate rock, we take essentially a calcium ion out of a carbonate rock and we put it back into a carbonate rock, and so there's no net lowering of CO2 or consumption of CO2 in that process. Okay, so rainwater, as you have gathered here, if you didn't know already, is naturally acidic. Naturally, it has a pH of about 5 to 6, maybe 5.5. So you can see out here in the plains and the Rocky Mountains, West Coast, where it's pretty homogeneous and we're pretty free of heavy loading of industrial pollution in these regions for the most part. You get pretty natural levels, like 5.5. Over here in the east, there's a lot of pollution. There are quite a few power plants that are burning coal that's rich in sulfur, and so there's quite a bit of sulfuric acid in the rain in this region. But there are also some natural reasons why why the rain is just generally lower pH in this region. But as you can see, in general, rainwater is quite acidic. And that is entirely the result, with the exception of sulfuric acid in this case, but it's entirely the result of absorption of CO2 or dissolution of CO2 from the atmosphere into rainwater as it's falling, right? And then that carbonate equilibrium after that, allowing carbonic acid to dissociate into hydrogen and bicarbonate. Okay. So that's the long-term carbon cycle, right? Carbon dioxide can dissolve in rainwater, react with rocks to produce carbonate ion or bicarbonate ion. It also produces calcium ion that combines to produce limestone or carbonate rocks in general. CO2 can also absorb or dissolve straight out of the atmosphere into the ocean or back from the ocean into the atmosphere. It can exsolve. That carbonate rock on the seafloor is going to remain there until it's forced down through a subduction zone and it's volatilized and returned to the atmosphere through volcanism and metamorphism, right? Mid-ocean ridges are also returning CO2 to the atmosphere, all right? And so we have this long-term carbon cycle that we've talked about and the short-term carbon cycle now, right? And so there are quite a few reservoirs at Earth's surface that contain carbon, they're spanning a massive, 7 orders of magnitude in size. All right, they're huge differences, and they're generally huge, right? The smallest thing we're looking at here, we're talking about atmospheric methane. It's very low in concentration. There's about 5 gigatons of it there. Limestone and sedimentary rocks, on the other hand, there's about 40 million gigatons of carbon stored in limestone and sedimentary rocks. Similarly, there's 10 million gigatons of organic carbon stored in sedimentary rocks, right? Oceanic bicarbonate there, 37,000 gigatons. That's the next biggest reservoir, is oceanic bicarbonate. Remember, that's that HCO3 ion. Fossil fuels, we're just using octane there. Fossil fuels is slightly smaller than that, or quite a lot smaller than that actually. Similar to the amount of carbonate sediments that are just sitting on the ocean floor that have yet to become rock. And so you can go through this. You can see that here's the oceanic carbonate ion and oceanic dissolved CO2. That's dissolved CO2 is essentially the same as saying carbonic acid. And so what we just learned with carbonate equilibrium is that these dissolved CO2, carbonate ion, and bicarbonate ion are in equilibrium with one another, those three, carbonate equilibrium. And you can tell here, most of it, almost all of it, is existing as bicarbonate, right? 37,000 compared to 740 and 1,300. That says right there that ocean water is pretty neutral, right? That's what that's saying. Okay, so that's what the reservoirs sort of look like, right? And so far we've talked about really 3 reservoirs: the atmosphere, sort of the biosphere or biomass, and sedimentary rocks. And we talked about quite a few processes that cycle carbon between these reservoirs. Specifically, we talked about 2 processes that cycle carbon between the atmosphere and the biosphere, right? Photosynthesis and respiration. And we talked about 2 processes that cycle carbon between the atmosphere and the sedimentary rock record or reservoir. Chemical weathering takes atmospheric carbon and turns it into sedimentary rocks, and volcanism and metamorphism, and really weathering as well, turn sedimentary rocks back into atmospheric carbon. Okay, and so you have 2 cycles here. The long-term and short-term carbon cycle, right? And they operate on very different timescales. The long-term carbon cycle, sedimentary rocks can exist for millions to billions of years. The short-term carbon cycle operates on days to weeks to seasons, years in some cases, but biomass generally doesn't stick around for very long. It doesn't live for very long, and once it dies, it's degraded fairly rapidly. There is one process that connects these two. It's called organic matter burial, and it's super important. It's going to take biomass out of the short-term carbon cycle and put it into the long-term carbon cycle. Okay, so organic carbon in sedimentary rocks here is the second largest reservoir, right? It's a quarter of the size of limestone. And so that organic carbon gets there through this process of organic carbon burial. And further, organic carbon in sedimentary rocks can be converted into fossil fuels through burial and associated heat and pressure. Okay, so organic matter burial, though almost all the organic matter produced through photosynthesis, primary production is what we call that, is respired back into CO2, about 99%. Really greater than 99%. A very, very small fraction is buried in sediments and becomes part of the sedimentary rock reservoir. This process represents a leak from the short-term carbon cycle into the long-term carbon cycle. All right, that's really important. Buried organic matter remained locked within a rock until the rock erodes, at which point it can weather chemically back into CO2, oxidize back to CO2. However, this is going to take a really long time, right? Because the organic matter is going to be buried on the seafloor, and then through tectonics, that seafloor is going to be eventually subducted or end up in some type of a convergence zone where mountain building processes are going to uplift that rock and expose it subaerially, or it's going to be forced down through subduction. And so this can take millions to billions, hundreds of millions of years for this to happen. And so this this buried organic matter is going to remain locked there, locked away, which is really important. It's, the point here is that it takes a really long time. That's what it says here. It takes a very long time for this to be exposed and reoxidized. And so despite the fact that it's a teeny tiny little fraction of total primary production that gets buried, the amount of organic matter buried in rocks is extremely large. All right, and this is super important here because oxygen is produced through photosynthesis and used up during respiration. The 20% of our atmosphere that's currently made up of oxygen is a direct result of organic matter burial. It's also a result of the standing biosphere, right? Every molecule of reduced carbon in the biosphere currently represents a molecule of CO2 that used to be in the atmosphere, and as a result, a molecule of oxygen that is currently in the atmosphere, right? Unless it's been subjected to other chemical reactions, which it is, right? And so if photosynthesis just stopped entirely, there would be no oxygen in the atmosphere within years, decades to centuries, I would think. It would be used up very rapidly through the oxidation of crustal material and reduced gases that come out of volcanoes and similar things. Okay, so primary production is photosynthetic production. Those are synonymous, essentially. The biosphere refers to this part of the earth that supports life, okay? And that includes the life itself, but it also includes all the things that support life. So the oceans, the atmosphere, land surfaces, et cetera, et cetera. At the base of any ecosystem is primary producers. These organisms are fixing carbon. I used that term earlier. Fix carbon just means take carbon dioxide and turn it into organic matter. Okay, and that is carbon fixation, and it's just a jargony way of saying an organism that can do photosynthesis or chemosynthesis. It can take carbon dioxide and turn it into organic matter, because it's very rare that organisms can do that, right? It's only these primary producers that can. All right, primary production is mostly accomplished through photosynthesis, though other carbon fixation pathways exist. Chemosynthesis uses energy to reduce CO2 that comes from naturally occurring redox gradients, okay? And so you need energy in order to fix carbon, in order to reduce CO2, and that energy in photosynthesis comes from light. In chemosynthesis, a very similar analogous process, that energy is coming from chemical reactions, redox reactions that are possible in the environment because of naturally occurring redox gradients. They occur in places like hydrothermal vents, hot springs, stuff like that. Organisms that can fix carbon are known as autotrophs. So this word troph means eating, and auto means of self, obviously. And so an autotroph is something that creates its own food, i.e. something that photosynthesizes or chemosynthesizes. Everybody else is doing what's called heterotrophy. Those organisms are known as heterotrophs. That just means that they eat or they obtain their carbon from outside, from others. And so they're consuming organic matter produced by other organisms to obtain energy and reduce carbon. Okay, and so they could be eating primary producers, or they could be eating other things. They could be eating other heterotrophs. Okay, so primary production, in addition to carbon dioxide, it requires a lot of other elements, right? Organic molecules essential for life also contain many other elements in addition to carbon. These elements come in many forms, but generally we refer to them as nutrients. Life needs much more of some elements than others, obviously. Most notably, these two, phosphorus and nitrogen. We use a ton of phosphorus and nitrogen, and so things like phospholipid bilayers. So all of our cells are surrounded by cell membranes, and all of the little internal structures, organelles and vesicles, things that make our cells operate, they're all surrounded by these membranes. And the membranes are composed of these phospholipids. And I'm sure you've all heard that term before, phospholipid bilayer. You probably learned it in elementary school or high school maybe, but they're these cell membranes, and it's a phospholipid. There's a lot of phosphorus in there. Similarly, there's tons of nitrogen used in DNA. There's lots and lots of nitrogen in these DNA backbones. There's nitrogen and phosphorus everywhere in your cells. We need tons of it. In fact, there's this very famous ratio, 106 to 16 to 1. That is that's the carbon to nitrogen, carbon to nitrogen to phosphorus. So 106 carbons to 16 nitrogens to 1 phosphorus. That's the average ratio of these elements in marine phytoplankton. But most life is pretty close to that. You're not going to get too far away from this ratio. That's known as the Redfield ratio. That's a very famous observation in chemical oceanography. Okay, so these nutrients, phosphorus and nitrogen in particular, but really all nutrients, come from the breakdown of continental rocks initially, and then they're for the most part they're recycled repeatedly in the environment. There are a select group of primary producers that are able to do something called nitrogen fixation, able to perform a process called nitrogen fixation, where they utilize atmospheric N2. Legumes can do this on land. They do it symbiotically. Cyanobacteria are the main culprits doing this in water, in aqueous ecosystems. So nitrogen fixation is taking N2 out of the atmosphere and incorporating it directly into organic matter. Now that's really helpful because the atmosphere is composed about 80% nitrogen, right? The atmosphere is about 80% nitrogen and about 20% oxygen. And so if you could take nitrogen out of the atmosphere, that would be a heck of an advantage. All other living organisms have to use nitrogen that's already been fixed. It's generally in one of these two forms, ammonium or nitrate. Okay. And so because there's this essentially limitless supply of nitrogen in the atmosphere and this process of nitrogen fixation, the limiting nutrient in most environments is phosphorus, at least on long time scales. So if the ocean has abundant phosphorus but no nitrogen, cyanobacteria and other nitrogen fixers will come in and fix nitrogen until they reach essentially the Redfield ratio, until they reach a level where nitrogen is no longer limiting production. Okay, and so on long time scales, phosphorus is generally thought of as the limiting nutrient, and it is exclusively coming from the breakdown of continental rocks. Delivering it to the oceans, and then it gets recycled over and over in the ocean. All right, so we'll talk a little bit about how these marine ecosystems are structured, and then I think we'll wrap it up for today, and we'll return to this discussion to talk a little bit more specifically about life and some feedbacks that exist in these systems in the next lecture. Okay, and so I drew you guys a little picture here. Hopefully it describes the situation pretty well. So light only penetrates about 200 meters of the upper water column, right? We call that area the photic zone. So the ocean kind of looks more like this, really. It's very dark, most of it. But that upper 200 meters or so is light. Okay, and so as you can imagine, there's lots of photosynthesis occurring up in the photic zone. There's photosynthesis to the extent that nutrients will allow, right? It is generally limited by nutrient availability, nutrient limitation. Okay, there's also lots of respiration taking place. Organisms are primary producers are photosynthesizing, they're being eaten and respired, they're dying and being broken down by bacteria through respiration, et cetera, et cetera. Okay, primary producers in the ocean are diverse, for one thing. There are a couple of classes or couple of groups that really dominate in today's ocean. One of them is the diatoms. And diatoms are these little single-celled organisms. They're photosynthesizers, obviously. They make their shells out of SiO2 silica, and they're quite pretty, kind of like little snowflake shapes, little wagon wheels. They're quite pretty little shells, but they're very, very small. They're quite abundant. Another really abundant group is the coccolithophores. So these are coccolithophorids, Emiliani huxleyi in particular, a very famous coccolithophorid, and these guys make little scales out of calcium carbonate, right? And so the scales, calcium carbonate, are inorganic carbon, right? The cell itself is organic carbon, the biological material, but these calcium carbonate scales are inorganic carbon, right? And so they exist in this organism at about a 4-to-1 ratio, the amount of organic carbon to inorganic carbon. And you can imagine that when this little guy dies, these little scales fall off and they sink down at the bottom of the ocean, carry some organic matter with them, etc. Okay, so complex food webs exist in most productive environments, beginning with primary producers, autotrophs. Those are then consumed by heterotrophs. Some heterotrophic organisms eat other heterotrophic organisms, right? Fish eat snails, snails eat algae. That's the food chain or the food web. These levels are known as trophic levels, right? So algae are in a trophic level below snails, which are in a trophic level below fish. Mostly ecosystems have about 4 trophic levels. These guys, zooplankton, are free-floating consumers in the ocean, so they're the first trophic level above primary producers. These are radiolarians, these are foraminifera. They're just 2 very, very dominant groups of primary consumers in the ocean today, known as zooplankton. So they're these single-celled, free-floating organisms, pelagic organisms. So like I said, more than 99% of organic matter generated through primary production is respired back into CO2. Eventually, much of this is accomplished by decomposers, these heterotrophic bacteria, in which nutrients are released back into the environment. Anything that is not subjected to respiration at some point is going to get buried in sediments, right? All right. So organic matter is being produced through photosynthesis in the photic zone. All right. There's lots of respiration here that takes place, and so there's lots of cycling, internal cycling. Okay. But a tiny fraction of this photosynthetic production is going to sink down below the photic zone. You can see there's kind of this debris that's floating downward here. This transport of organic matter out of the photic zone is known as export production. Okay, and it's really important because down here below the photic zone, there's no sunlight for photosynthesis to take place. So there's photosynthesis and respiration up here in the photic zone, but down here in the aphotic zone, or in the deep ocean, there is respiration only. Okay, and this becomes more important because remember, as we learned before, there's this sharp density contrast between deep ocean water, which is more dense, and shallow ocean water, which is less dense. Okay, and these 2 bodies of water, the shallow ocean and the deep ocean, generally don't mix. They're pretty effectively physically stratified because of this density contrast, which really results from temperature and salinity, as we learned previously. Okay, and so you have this downward settling of organic matter out of the photic zone, out of the surface ocean, into the deep ocean. All right, it's physical transport of organic material, and anything else that's associated with the organic material is being physically transported downward into the deep ocean. All right, and we have a special name for this. It's the biological pump, right? And what the biological pump really does is it pumps, quote unquote, pumps organic matter and probably more importantly, nutrients downward from the surface ocean into the deep ocean, okay? And so as that organic matter sinks, it's subject to respiration, obviously, but it is respired, it's broken down. And so as you move lower and lower in the water column, there's less and less organic matter remaining. And so if you looked at kind of versus depth, you had photosynthesis, it would look something like that. Lots of photosynthesis in the surface ocean, none below it. Respiration would look like this. There's quite a lot of respiration in the photic zone as well, and then it sort of just decays, or kind of gradually decreases as you move downward. Okay, so here's a figure from a textbook of the biological pump. You have photosynthesis, you have heterotrophs producing fecal pellets, you have photosynthesis producing oxygen, right? That's photosynthesis. This molecule here, CH2O, it says it here, it's a common abbreviation for organic matter. It's a sugar, right? CH2O is the form for a sugar, like C6H12O6, right? So that's photosynthesis, oxygen production. Then you have settling of organic matter downward into the deeper ocean. And you have some processes occurring down here. Decomposition, that results in nutrient release and oxygen consumption, right? CH2O plus O2 results in CO2 and water. That's respiration. It's consuming oxygen. It's also releasing any nutrients that are associated with this organic material, which is really important, right? Because those nutrients can just build up down here in the deep water until they're brought back to the surface through upwelling or some similar process. Okay, and so the decomposition of single organic matter releases nutrients, and it results in a nutrient profile in the ocean that looks something like this. It's very, very low in the surface ocean, but in the deep ocean, it's quite a bit higher, right? And it spikes just below the photic zone where the most respiration is taking place, in this zone right here. So that's super important for anywhere on the Earth where deep ocean water comes back up to the surface, a process that we learned a lot about and we call upwelling, right? It happens in coastal regions quite frequently because of these offshore currents that push surface water away from the shore due to Ekman transport, and then deep water is able to come up and fill in. Those are generally really, really productive environments because there's this constant delivery of nutrients from deep ocean water up to the surface. Okay, and so the coast of California is one of those upwelling zones. Here's kind of a distribution. So this is satellite data that shows the distribution of chlorophyll in the world's oceans, and what you can see is that it's not distributed evenly, right? It's very specific where high chlorophyll concentrations are found. They're found right along the equator due to this equatorial upwelling, divergence associated with Ekman transport away from the equator in both directions due to the trade winds, right? The trade winds are blowing from east to west across the ocean here, north and south of the equator. Because of Ekman transport, water is being pushed away from the equator in this direction in the north, away from the equator in this direction in the south, and it's causing divergence right along the equator, which allows for upwelling to take place. Similarly, on the west coasts of most of the continents, you have these eastern boundary currents. They're bringing cold water from high latitude down the west coast of the continents, and in the process, they're pushing water offshore, pulling it away from the coast. And as it does that, deep water is able to come up and fill in. You can see that that process is really efficient along the Namibian coast down here in southern Africa and kind of in this Central African region. It's also incredibly powerful down here in Central America and northern South America up here. So it's obviously extremely important where upwelling occurs. It controls the distribution of life in the oceans pretty much directly. Another process that's important here, there's a lot of production up here at high latitudes, and a lot of that results from just sort of the free upward and downward movement of water at high latitudes because the thermocline breaks down. And without a strong thermocline, like we talked about, you can have production of deep water through the formation of sea ice, and increasing salinity because of sea ice can cause water to sink down to the bottom of the ocean to form new deep ocean water. You can similarly have deep ocean water coming up to the surface because although it's very dense, the surface water gets very dense at high latitudes because it's so cold. And so you have kind of free exchange upward and downward of water at high latitudes, which results often in high nutrient content of surface water at high latitude and consequently high production, right? Okay, so if we return back to our margin here, we have lots and lots of production in the photic zone. We also have lots of respiration up there, but we have some export production, right? We have the biological pump causing organic matter to settle downward under the influence of gravity out of the photic zone and into the deep ocean. As you do that, you get lots of respiration just below the photic zone, and that respiration is consuming oxygen, right? And so if you look at a dissolved oxygen profile of the ocean under a productive margin, what you'll find is that in the photic zone, oxygen is really high. But as soon as you get down below the photic zone, it drops dramatically. It'll reach some minimum and then likely rebound. If production is high enough, you can actually get oxygen dropping all the way to zero, a condition we call anoxia, where there's no dissolved oxygen in the water. And this condition occurs frequently along continental margins just beneath highly productive regions. And we have a special term for it. It's called an oxygen minimum zone. And it's really important. Our research group studies oxygen minimum zones quite a lot. It turns out that while there's 20% oxygen in the atmosphere today, the Earth was not always like that. As you go backward in time, past about 2.5 billion years ago, there was no oxygen in the atmosphere at all. And even more recently than that, up until about 7 or 800 million years ago, it appears that oxygen was quite low. And perhaps remained that way even long into the Paleozoic, to be honest. But those are topics of really active research, and it's one thing that we study very. It's one of the main topics of our research group is reconstructing the oxygenation history of the Earth. And so it's tough to find places near the surface today that are anoxic, though they do exist. And so we study them in detail in order to learn things about water and sediment chemistry under those conditions so that we can apply them to the ancient record when much more of the ocean was characterized by these anoxic conditions. Okay, in any case, this is what oftentimes results. This, is always kind of what's happening at a continental margin. You have lots of photosynthesis up in the photic zone, and you have settling of organic matter down into deeper water, and lots of respiration as a result. The nutrient profile reflects that, and so this is the short-term carbon cycle, right? In the marine realm, at least, which is where the short-term carbon cycle existed exclusively for the majority of Earth's history. It's only a fairly recent advent that we have life on land. And so, this is the short-term carbon cycle. And you can see that as organic matter is produced in the photic zone, it's going to settle downward. But the ocean is really deep. And so the majority of this organic material is going to be respired. Very, very, very little of it is going to make it down to the sediments and be buried in the sediments. But some very small fraction does get buried in the sediments, and then it stays there until it's exposed somehow or recycled through subduction. And so that really, that really is the long and the short-term carbon cycle. Next time, we're going to talk a little bit more about life and biomass and the distribution of life. But mostly what we'll talk about are feedbacks that exist in these systems. So feedbacks that exist between photosynthesis, respiration, atmospheric CO2 and biomass, really, and temperature, feedbacks that exist here in chemical weathering, volcanism and metamorphism, and temperature. And we'll talk a little bit more about how this process occurs and how it drives long-term climate. So thanks very much, and I will see you soon.